All right, let's get started. In this video, I'm going to go over section 7.2. Section 7.2 is about limits of sequences. Okay, basically, I will be starting by defining the limit of a sequence. Okay, from this section onwards, I'm going to use these symbols. This is the symbol for there exist. Okay, whenever I want to write there exist, I write this symbol. Whenever I want to write for all, I'm going to write this symbol, and this is of course such that. Okay. All right, I want to start with this definition. What do you mean by a sequence converges to a real number L? Okay, so let's go over this definition. Definition 7.8. Suppose AK is a sequence of real numbers. We say that the limit as k goes to infinity, AK is equal to L for some real number L, or equivalently, we write this statement, AK goes to L as k goes to infinity, if for any epsilon greater than 0, there exists some n greater than 0, such that if you choose your k to be bigger than n, then your AK has to be between L minus epsilon and L plus epsilon. Okay, you should be able to find such an n for any given epsilon greater than 0, such that your AK is stuck between L minus epsilon and L plus epsilon. Okay, if that is the case, we say that this limit statement is true, or in other words, limit as k goes to infinity, AK is equal to L. Okay, and here I want to give this remark. If limit as k goes to infinity, AK is equal to L for some real number L, then we say that the sequence converges to L. If you can find this limit as a real number L, then we say that our sequence AK converges to that real number L. If no such L exists, then we say that the sequence diverges. Okay, let me quickly give you an example for a divergent sequence. Think about this sequence. What happens when k goes from 1 to infinity? These terms are getting arbitrarily large, right? The sequence is namely 1, 2, 3, so on and so forth. There is no bound here. It's growing arbitrarily large, right? So the limit does not exist. Or in other words, this limit approaches to infinity. Infinity is not a real number. Okay, infinity is not a real number. Here in this case, limit as k approaches to infinity, AK is k. This is your AK is equal to infinity. Infinity is not a real number, so we say that this is a divergent sequence. Okay, if it is convergent, of course, this limit should exist as a real number. It cannot be infinite. Okay, this is an example of a divergent sequence. All right, what do we mean by this limit statement geometrically? Okay, here is the geometrical idea. Limit as k goes to infinity, AK is equal to L means your sequence, if I put my AK, the sequence values on the y-axis and the k values on the x-axis, that means this limit statement means as k is getting larger and larger, your AK values are getting closer and closer to the L. This is the value L. As you can see, these values are getting closer and closer to L. For any given epsilon greater than 0, your AK has to be between, for any given epsilon greater than 0, you should be able to find n greater than 0, such that if your k is bigger than n, your AK has to be between L minus epsilon and L plus epsilon. Look at this diagram. If you take L here, let's say your L plus epsilon is here, okay, for any given epsilon, and L minus epsilon should be below L, of course. And then can you find an n such that if you choose your k to be bigger than n, then your AK is between L minus epsilon and L plus epsilon. As you can see, if I take this particular value to be my n, as long as you pick your k value bigger than n, your sequence value is between L plus epsilon and L minus epsilon and L plus epsilon. For example, if you take your k value to be here, here is your sequence value of the sequence, which is in fact between these two numbers, L minus epsilon and L plus epsilon. As long as you pick your k value to be bigger than n, your sequence value is between L minus epsilon and L plus epsilon. Okay, that's the idea. This has to be true for any epsilon. So that's the geometric idea of the limit, existence of the limit. All right, let's move on. Next, we have this theorem, theorem 7.9, limits of sequences defined by continuous functions. Okay, let AX be a function that is continuous on the interval 1, infinity, and AK be the sequence defined by AK is equal to A of K for all K positive integers. If limit as X approaches to infinity, A of X is equal to L, then the limit as K approaches to infinity, AK should be L. Okay. So what does this mean? First of all, notice that the sequence AK is obtained by plugging positive integers in this function AX. Okay. AX is given to be a continuous function. Okay. The sequence AK is obtained by plugging positive integers to this function. As you can see here, AK is equal to A of K. K is a positive integer. Okay. Now, what does the theorem say? If this limit statement is true, then this has to be true. That's what it says. Okay. If limit as X approaches to infinity, A of X is equal to L, then limit as K approaches to infinity, AK should be the same as L. Okay. Let's prove this theorem. Okay, let's prove this theorem. We are going to assume that this limit statement is true. Okay, then we have to show this is true, right? So let's assume that this is true. Assume that this limit statement is true. Okay, now in order to show that limit K as K approaches to infinity, AK is equal to L, what do we have to show? By definition of the convergence of a sequence, this is the definition of convergence of a sequence. We say that limit K approaches to infinity, AK is equal to L. If for any epsilon greater than 0, if we can find n greater than 0 such that if K is greater than n, then AK is between L minus epsilon and L plus epsilon, right? That's what we need to show. We must show that for any given epsilon greater than 0, there exists n greater than 0 such that AK is between L minus epsilon and L plus epsilon for all. This is the symbol for all, okay? For all K greater than n. That's what we need to show. Well, to show that, let's take any epsilon greater than 0. Take any epsilon greater than 0. Then we are assuming that this limit statement is true. Then by section 1.3, let me check the section. Yeah, section 1.3, definition 1.9. It's in calculus 1. Okay, you might want to review those notes. Calc 1, section 1.2, definition 1.9. There exist, by this particular definition, there exist n greater than 0 such that your A of X is between L minus epsilon and L plus epsilon. Okay, that is because this limit statement is true. Since this limit statement is true, by this particular definition, there exists n greater than 0 such that A of X is between L minus epsilon and L plus epsilon for all X greater than n. If this is the case, I can write AK, pardon me, if I plug in a positive integer, which is bigger than n, still this should be between L minus epsilon and L plus epsilon, right? Why is it true? Because AX is between L minus epsilon and L plus epsilon for all real numbers X greater than n. Then AK should be between L minus epsilon and L plus epsilon for all positive integers greater than n. Okay, if this is true for all X greater than n, it has to be true for all positive integers K greater than n. Okay. All right, what does this mean? This means we have found an n such that ak is between L minus epsilon and L plus epsilon for all k greater than n. That means this limit statement is true by definition. That means limit as k goes to infinity, ak has to be L by definition. For this given epsilon greater than 0, we found an n such that whenever your k is bigger than n, your ak is stuck between L minus epsilon and L plus epsilon. That means this limit statement has to be true. Okay, this completes the proof. That's what we wanted to prove. All right, let's move on. Next, we have another definition, definition 7.10, sequence that diverge to infinity or minus infinity. Okay, I'm going to give both definitions here. Suppose ak is a sequence of real numbers. We say that limit as k approaches to infinity, ak is equal to infinity, or equivalently we write ak approaches to infinity as k approaches to infinity. If for any m greater than 0, there exists n greater than 0 such that as long as you pick your k to be bigger than n, your ak has to be bigger than uppercase n. Okay, if that is the case, we say that this limit statement is true. Limit as k goes to infinity, ak is equal to infinity. Okay, before I go to my second definition, let me geometrically explain this definition. What do we mean by limit as k goes to infinity, ak goes to infinity? Here is the geometry. Take a sequence ak. Of course, sequence values are on the y-axis, k values are on the x-axis. Take a sequence like this. I have marked down the points of that sequence. As you can see, as k is getting bigger and bigger, the sequence values are growing arbitrarily large. There is no bound. They are growing arbitrarily large. Okay, so that means as k goes to infinity, your sequence values are approaching infinity. This goes to infinity. This is getting higher and higher. There's no bound. Okay, that's what we mean by limit as k approaches to infinity, ak is equal to infinity. Okay, and here is the definition. Okay, this statement, this limit statement is true means for any given m greater than 0, you should be able to find n greater than 0 such that if k is bigger than n, your ak has to be bigger than m. Is it true for this picture? Can you find for any given m bigger than 0, can you find n bigger than 0 such that if your k is bigger than n, then ak is bigger than m? Well, let's see whether we can find it. For example, let's take your m to be somewhere here. You can take your m to be anywhere. Okay, it can be any large number. Okay, for instance, let's take your m to be here. Then our question is, can we find an n such that as long as your k is bigger than n, your ak is, pardon me, this one. As long as your k is bigger than n, your ak is bigger than m. Well, clearly, if I take my n to be this one, this particular number to be n, as long as you pick your k bigger than that n, for example, if you pick your k here, your sequence value is this one. That is clearly bigger than m. Your sequence value is clearly bigger than m as long as you pick your k values bigger than n, because all the sequence values are lying here as long as you pick your k values over here bigger than n. Okay, so that this definition is alive for this picture. And a similar definition holds for this limit statement. Limit as k approaches to infinity, ak is equal to minus infinity, or equivalently we write ak approaches to minus infinity as k approaches to infinity. If for any m greater than 0, there exists some n greater than 0 such that if your k is bigger than n, then ak has to be less than minus m this time. It's not m, unlike in the previous case, it's minus. Okay, so that means your sequences should be like this, right? The points of your sequence this time, it should be going down. This is your k axis, of course, this is ak. As when k is getting larger and larger, your sequence values are getting smaller and smaller, and it becomes very large negative numbers. There's no bound. Okay, in that case, we say that limit as k approaches to infinity, ak is equal to minus infinity. It's going to minus infinity. All right, let's move on. Next, I want to go over this theorem. This is a very, very important theorem. And this we can apply this theorem to solve many limit-related problems. Let's go over the theorem. Theorem 7.11, basic limit rules for convergent sequences. Okay, notice that these rules are for convergent sequences. Here is what the theorem says. If AK and BK are convergent sequences with limit as k approaches to infinity, AK is equal to L, and limit k as k approaches to infinity, BK is equal to M, and if C is any constant, these four statements are true. What is the first statement? Limit as k approaches to infinity, C times AK is equal to C times L. What this simply tells you is that if you have a constant, you can pull this constant out. If you pull this constant out, you have C times limit k as k approaches to infinity AK, but limit as k approaches to infinity AK is L. That becomes C times L. Okay, that's what it tells you. You can, if whenever you have a constant, when taking the limit, you can pull that constant out. And here is the second part. If you have summation of AK and BK, limit as k approaches to infinity, AK plus BK is equal to L plus M. Notice that your L is limit k approaches to infinity AK, your M is limit k approaches to infinity BK. Okay, so this is this limit and M is this particular limit. What this simply tells you is that you can distribute the limit. Okay, this limit you can distribute through the parentheses. You put the limit to the first term, this one, and then you put the limit to the second term. That's what this is about. Okay, L is equal to this limit and M is equal to this. And then here is the next statement. Limit as k approaches to infinity, AK times BK is equal to L times M. Again, what this tells you is that you can put the limit for each individual piece if you have a product. Okay, if you put the limit for AK, the limit of AK is L. And then if you put the limit for BK, limit of BK is M. That becomes L times M. And then the last one is, if M is not equal to 0, then the limit as k approaches to infinity, AK divided by BK is equal to L divided by M. What this tells you is that if we have a division like this, you can take the limit of the top and limit of the bottom separately. If you take the limit of the top, the limit of AK is exactly L, so L should be in the top. And if you take the limit of the bottom, limit of BK is M, so M should be in the bottom. Okay. All right, that's the idea of that theorem. I'm not going to prove all of the part, but I want to prove one of them. I will prove part B, and the other parts will be similar. Okay. Okay, so what do I want to prove in order to prove part B? First of all, part B says that if limit k approaches to infinity, AK is equal to L, and limit k approaches to infinity, BK is equal to M, then this limit has to be L plus M. How do we show that? This is the definition of limit, right? We say that limit k approaches to infinity, AK is equal to L, if for all epsilon greater than 0, there exists some n greater than 0 such that if k is bigger than n, then AK has to be between L minus epsilon and L plus epsilon. Now think of your AK as this particular thing. This is your AK. This whole thing is your AK this time. You need to show that this whole thing goes to this particular number as k approaches to infinity, right? How do we prove that using the definition? To show that, we must show that for a given epsilon greater than 0, for any given epsilon greater than 0, there exists n greater than 0 such that that sequence that I am interested in is between L plus epsilon, L plus M minus epsilon, and L plus M. This should be plus epsilon. Okay, this is a typo. This has to be a plus. This particular sequence has to be between this quantity minus epsilon and that quantity plus epsilon. L plus M minus epsilon, L plus M plus epsilon. Okay, so that's what we need to show. How do you show that? To show that, First of all, let's take any epsilon greater than 0. Then notice that if you take epsilon to be greater than 0, epsilon over 2 is also greater than 0, right? If you take any fixed epsilon greater than 0, epsilon over 2 is also a fixed positive number. Now, since this limit statement is true, notice that we are assuming that these two are true and we want to show this limit statement. If this is true, for this particular positive number, there exists some n1 such that AK is between L minus epsilon over 2. My positive quantity is epsilon over 2 this time, and L plus epsilon over 2. For all k greater than n1. This is n1, okay? Similarly, since this limit statement is true, there exists some n2. There exists. This is the symbol for there exist, okay? Remember that always. There exists n2 such that my bk is between m minus epsilon over 2, comma, m plus epsilon over 2. That is by the definition of limit for all k greater than n1. Okay, these two statements have to be true. You should be able to find some n1 and n2 such that these two things happen. Okay, what are we going to do now? Now I'm going to take my n to be the maximum of n1 and n2. I'm going to take my n to be the maximum of n1 comma n2. All right, now let me make a small observation here. Okay, your AK is between L minus epsilon and L plus epsilon for k bigger than n1. BK is between m minus epsilon and m plus epsilon over 2, pardon me, for k bigger than n2 here. This is a typo, this should be n2. Okay, that means this should be in this interval for k bigger than n, right? Because n is a number bigger than or equal to n1, because I take my n to be the maximum of n1 and n2. That means this has to be true even if you choose your k bigger than n, because n is a number bigger than or equal to n1. Okay, so I can write AK is between L minus epsilon over 2, comma, L plus epsilon over 2, and your BK is between m minus epsilon over 2, comma, m plus epsilon over 2 for all k greater than n. That's because your n is bigger than or equal to both n1 and n2. As long as you pick your k bigger than n, that means your k is bigger than n1 and it is bigger than n2. So that means this AK should be in this interval and BK should be in this interval. Okay, what does this tell you? This tells you something interesting. Let me make an observation here. This means AK has to be strictly greater than L minus epsilon over 2 and strictly less than L plus epsilon over 2. That's what we mean by AK is between these two numbers. Similarly, here BK has to be strictly bigger than m minus epsilon over 2 and it should be strictly less than epsilon over 2. Now I'm going to add these two inequalities. This is inequality 1, this is inequality 2. If you add 1 plus 2, what would that give you? That gives you AK plus BK in the middle, of course. Here in the left hand side, you have L plus M minus epsilon. Notice that here you have epsilon over 2, here you have epsilon over 2, minus epsilon over 2. And when you add those two together, you get epsilon here. And then in the right hand side, you have L plus M plus epsilon, of course. What does that tell you? That tells you that AK plus BK is between L plus M minus epsilon, comma, L plus M plus epsilon for all K bigger than N, because these two statements are true when K is bigger than N. Doesn't that prove that this limit statement? That's the definition of the limit statement. This is true. We found N, some N, positive N, such that as long as you pick your K to be bigger than N, your AK plus BK is between these two numbers. That's what exactly we wanted to prove. Okay, this establishes the result. Okay, this limit statement is true. This limit statement is true. All right, let me actually write it in a formal way. So that means that implies limit K approaches to infinity, AK plus BK is equal to L plus M. Okay, this completes the proof. By the way, this arrow is used to say implies. Okay, arrow means implies. All right, next I want to go over this particular example. Show that limit as K approaches to infinity AK plus limit K approaches to infinity BK that does not necessarily equal to limit as K approaches to infinity AK plus BK. Okay, necessarily equal to this limit for divergent sequences AK, BK. Okay, if the sequences are divergent AK and BK, then this doesn't have to be equal to this one. Remember, if they are convergent, in the previous theorem, we proved that has to be equal, right? Remember, this limit has to be equal to summation of these two limits, these two particular limits. Okay, but that is not true if the sequences are divergent. If these two sequences are divergent, that's not true. That's what we are going to show here. Okay, we are going to provide an example of two sequences, divergent sequences, with this limit is not equal to, the summation of these two limits is not equal to this limit. Okay, so I'm going to take my AK to be minus 1 to the power K, and I'll take AK BK to be minus 1 to the power K plus 1. Okay, let's see what happens for each statement. Let's see what happens with this one. Okay, as you can see, this is an oscillating sequence, right? This sequence is, if you write out AK, sequence AK, it is going to be minus 1, 1, minus 1, 1, so on and so forth. BK is going to be 1, minus 1, 1, minus 1, so on and so forth. As you can see clearly, these are divergent sequences, right? Because it does not approach a particular value as K approaches to infinity, because these are oscillating between, terms are oscillating between minus 1 and 1, right? That means they are not approaching a single value. Okay, this is a divergent sequence. This is also a divergent sequence. So this summation is divergent. This summation does not exist. Limit K approaches to infinity AK plus limit K approaches to infinity BK does not exist. Why doesn't it exist? Because this does not exist, because this sequence diverges, and this does not exist. So the summation does not exist. Okay. What about this one? Would this exist? It better exist. We want to show that this summation is not equal to this one, right? So let's see whether we get something different there. So let's calculate that. We want limit as K approaches to infinity AK plus BK is equal to limit K approaches to infinity. AK is minus 1 to the power K plus BK is minus 1 to the power K plus 1, right? This is equal to limit K approaches to infinity. I can pull out a minus 1 to the power K because minus 1 to the power K is common. Then you get 1 plus minus 1. But what is 1 plus minus 1? 1 plus minus 1 is 0, right? That means 0 times this whole thing is 0. So this limit is 0. Notice that this limit is 0, but this limit does not exist. So that means these two are not equal, right? So we provided the count example to show that when the sequences are divergent, these two things doesn't have to be equal. Okay, this is a very good count example. All right, let's move on. Next, I want to go over this particular example. Use previous theorem to find the limit of the sequence as K approaches to infinity. Okay, previous theorem, by previous theorem, I refer to this theorem. Okay, how do you use this theorem to find the limit here? Well, we have a quotient here, right? If we have a quotient, this probably we will be applying this part, right? Because we have a quotient here. So we need to find the limit of this quotient. To find the limit of this quotient, what you do is take the limit of the top and take the limit of the bottom, right? And then you have the quotient of those two corresponding limits. That's what we are going to do here. But we cannot apply the limit straight away. To find the limit of an expression like this, we are using some strategies to find the limit. Okay, here is the strategy. You might be familiar with these kind of strategies when you do your calculus 1 class. You should have seen some of these things. We need K as K approaches to infinity, K minus 2 divided by K squared plus K minus 7. That's what we are asked to find. Okay, so the trick here is, before you get the limit, if you try to get the limit straight away, if you plug in infinity in the top and infinity in the bottom, you get infinity over infinity. That's indeterminate form, right? So it doesn't give any information. So to avoid that trouble, what we do is limit K approaches as K approaches to infinity. I'm going to divide both top and bottom by the highest degree term. If you look at both top and bottom, the highest degree term is K squared, right? So I'm going to divide both top and bottom by K squared. K minus 2 divided by K squared. I divided my top by K squared. I divide my bottom also by K squared. That's the trick that we are using. Always the highest degree term. You divide top and bottom by highest degree term. Now let's do some simplification here. Limit as K approaches to infinity. In the top, you have 1 over K minus 2 over K squared, right? I'm dividing each individual term by K squared. I do a similar thing to the bottom, then you get 1 plus 1 over K minus 7 over K squared. Now you are ready to take the limit. Now let's take the limit. What happens as K approaches to infinity for this one? Your denominator is approaching to infinity. That means this whole thing is 0, right? Here also the whole thing is 0. So in the top you have 0 minus 0. In the bottom, what do you have? 1 is there. When you take the limit as K approaches to infinity in the bottom, here the limit of 1 is just 1, right? It's a constant. What is the limit of this one? That's 0. And then minus again 0. As K approaches to infinity, this also becomes 0. Okay, so the value here is 0. That's the limit value. Okay, where did we apply this theorem then? In that computation, where did we apply this theorem? Well, to get the limit here. To get the limit here, you have to get the limit of the top and the limit of the bottom. So you apply the limit to the top and you apply the limit to the bottom. Applying the limit to the top, you get 0 in the top, and applying the limit to the bottom, you get this quantity in the bottom. This is in fact 0 over 1. 0 over 1 is 0. All right, let's move on. Next, I want to go over this theorem. Some more limit rules. Suppose AK is a sequence, limit of functions of sequences. Okay, this is what the first part tells you. Limit as k approaches to infinity, AK is equal to L, and F is a function that is continuous at L, then limit as k approaches to infinity, F of AK is equal to F of L. Okay, what this rule tells you is that if your function F is continuous and if this limit statement is true, to get the limit of this one, to get the limit as k approaches to infinity F of AK, you send this limit inside the function. You send this limit over here. You just take the limit of AK, but the limit of the AK is given to be L. That becomes, this whole thing becomes F of L. Okay, that is the first part. And then the second part is about uniqueness of limits for sequences. You cannot have two finite limits for sequences. If, here is the statement, if limit as k approaches to infinity, AK is equal to L, and limit as k approaches to infinity, BK, this is a typo, it should be BK. BK is equal to M. Oh, no, it's not a typo, pardon me. Okay. Limit as k approaches to infinity, AK is equal to L, and limit as k approaches to infinity, AK is equal to M, then L has to be equal to M. You cannot have two different limits for the same sequence. If the sequence is same and the limit exists, that limit has to be unique. The limits L and M should be the same. And then this is the third part. Again, this is a very, very useful theorem to find in calculating limits of certain sequences. Okay, the squeeze theorem for sequences. You should be familiar with some sort of squeeze theorems when you were taking your calculus 1 class. Okay, there also you did a squeeze theorem, but this theorem is very similar to that. Okay, here is what the theorem says. If mk, lowercase mk and uppercase mk are sequences that both converge to L, and if AK, if the sequence AK is stuck between mk and lowercase mk and uppercase mk for all k, then the limit of the sequence AK also has to be L. Does that make sense? This theorem says that if the limit of this sequence and this sequence, both of these sequences are, the limits of both of these sequences is L, then the limit of this sequence also has to be L. Okay, that is the squeeze theorem. And then the last part, limit of absolute value sequence. Okay, this is what the that part tells you. Limit as k approaches to, if the limit as k approaches to absolute value of AK is equal to 0, then the limit of the original sequence has to be 0 as well. Okay, if the limit of this absolute value sequence is equal to 0, then the limit of AK itself has to be 0. Okay. All right, let's move on. Next, we have this definition of a subsequence. Okay. Before I give the definition, let me give you a rough idea about what we mean by a subsequence. Subsequence means, suppose you are given a sequence AK. This is A1, A2, A3, so on and so forth. Then the subsequence means, let's label subsequence by AKN. Okay. Subsequence means some subcollection of this sequence. So it could be something like this. I take A2, A4, A6, so on and so forth. As you can see, here we don't have all the numbers that you have here, but I have a subcollection of numbers in the ascending order. A2 is here, and then A4, and then A6, and so on and so forth. Okay, it's simply this is called a subsequence of your original sequence. And here is the definition. AK be a sequence, and F is a strictly increasing function from set of positive integers to itself. Then the sequence A of AFK is called a subsequence of AK. Okay, AFK means this FK is the subscript here. When you write AFK, FK is the subscript. Okay, this AFK will give you a subsequence of AK, provided F is an increasing function, strictly increasing function from C+ to C+. Let me give you an example. Okay, I'm going to take my FK to be 2k minus 1. Then you can easily see that this is an increasing function, right? When you put the bigger and bigger k values, you get bigger and bigger function values, right? So this is an increasing function. Now, what is the subsequence given by this particular increasing function? To get that subsequence, this is of course A1, A2, A3, dot, dot, dot. To get the subsequence, I want to have my f of k as the subscript. How do I get the subsequence now? This is equal to A, f of k is 2k minus 1. Now, to get the subsequence, all what you need to do is you plug in k is equal to 1, 2, 3, 4, and so on and so forth. Okay. First, I plug in k is equal to 1 here. That will give you A1. And then I plug in k is equal to 2. If you plug in k is equal to 2, you will get A3, and then A5, A7, so on and so forth. Okay, so this is the subsequence. As you can see, this is a sub collection of elements in the original sequence. Okay, you just omit the even terms, right? That's all you do here. All right, that's about subsequences. Let's move on. Next, we have this theorem. Let AK be a sequence that converges to L. Okay, we are given that limit as k approaches to infinity, AK is equal to L. That's what we mean by AK be a sequence that converges to L. Then every subsequence of AK also converges to L. Okay, if you take any subsequence of this sequence AK, it should also converge to L. That's what this theorem tells you. If you visit back the previous sequence, if this original sequence converges to L, then the subsequence also should converge to L. That's what that theorem tells you. Okay. I'll cross this because this doesn't belong here. Okay. All right, let's move on. Maybe I will write limit as k approaches to infinity, your subsequence, A of f of k. Remember, A of f of k is your subsequence, right? This should also be L. That's all it says, okay? F is an increasing function as we defined in the previous definition. All right, let's move on. Next, I want to go over this theorem, theorem 7.15, convergence and divergence of geometric sequences. Okay, first of all, we are going to first talk about geometric sequences of this form. And as you have seen, the general form of a geometric sequence is going to be like this. K goes from 0 to infinity. But let's first deal with this particular form. Okay. In this case, basically, you take your C to be 1, right? If you take your C to be 1, this is what you get. Okay. For this geometric series, we have some criteria to determine whether the geometric series converges or diverges. Again, what do you mean by converges? What do you mean by this geometric series converges? That means the limit of this sequence should exist as a real number, some nice real number. Okay. If it doesn't exist, then it diverges. Okay. Here are the criteria. If the absolute value of R is bigger than 1, then this sequence R to the power K diverges. And if R is equal to -1, then also this sequence diverges. And if R is equal to +1, then RK converges to 1. And if R is absolute value of R is strictly less than 1, then RK converges to 0. Okay. So we need to know these 4 criteria to determine whether a given geometric series is convergent or divergent. Okay. All right. Let's move on. We'll be applying this theorem in some examples. Okay, next I want to go over this example, showing that a geometric sequence diverges. Show that the geometric sequence, this particular geometric sequence, diverges. How do we show that this diverges? Well, for contrary, assume that this particular sequence converges. K goes from 0 to infinity, converges. Let's assume that it converges, okay? And then we will come up with a contradiction, okay? Okay, if this converges, let's take, then there has to be some real number such that limit as k approaches to infinity. Okay, if this is convergent, there has to be some L real number such that limit as k approaches to infinity minus 1 to the power k is equal to L, that real number. Okay, and I'm going to take my epsilon to be 1 this time. Okay, then since this limit statement is true, for this particular given epsilon, I should be able to find there exists some n greater than 0. That is by the definition of the existence of the limit. Okay, there exists some n greater than 0 for this given epsilon greater than 0, such that minus 1 to the power k is between L minus epsilon and L plus epsilon for all k bigger than n. I'm just unwinding the definition of the limit. Okay, this limit exists. That means I should be able to find some n greater than 0 such that my ak is between L minus epsilon and L plus epsilon for all k greater than n. Okay, this implies that, what does this tell you? Notice that when k is odd, this is minus 1. When k is even, this is going to be plus 1. That means minus 1 and plus 1 has to be between L minus epsilon and L plus epsilon, right? Because there are odd and even numbers. When k is bigger than this particular n, there are both even and odd numbers, both even and odd case. That means both minus 1 and plus 1 are possible when k is bigger than n. That means minus 1 and plus 1 has to be in this interval. This implies, this arrow indicates that implies, okay? Minus 1 should be between L minus epsilon and L plus epsilon. Also, plus 1 should be between L minus epsilon and L plus epsilon. Now let me show you the geometry. Let's say your L minus epsilon is here on the real number line, and L plus epsilon is here. And this tells you that your minus 1 is between these two numbers. Minus 1 is between these two numbers. That means minus 1 has to be somewhere here. Similarly, plus 1 has to be between those two numbers. So plus 1 has to be somewhere here, right? This minus 1 and plus 1 should be strictly between this number and this number. Okay. But now notice that your epsilon is 1. I take my epsilon to be 1, right? That is for a reason. You will see why I'm taking that epsilon to be 1. Okay. So this implies that the distance between minus 1 and 1 is equal to 2. What is the distance between L minus epsilon and L plus epsilon? This distance is 2, right? Clearly it's 2. 0 has to be in the middle. Minus 1 to 1, the distance is going to be 2, right? You know, from your pre-calculus. What is the distance between these 2 points? Wouldn't that be 2 epsilon? Basically, to find the distance, you subtract this number from this number, right? If you subtract this number from this number, you get 2 epsilon. But what is your epsilon? That's 1, right? But notice that this distance has to be strictly smaller than the distance between these 2 points, right? That's because these 2 points are inside this interval, L minus epsilon and L plus epsilon. But it tells you that the distance between these 2 points is equal to 2. Pardon me, this should be 2, okay? Distance between these 2 points is 2, and distance between these 2 points is also 2. Is that possible? That's not possible, because -1 and 1 are inside this interval, strictly between these two numbers. This is not possible, okay? So this is a contradiction. So this is a contradiction, means our assumption is not correct. This does not converge, okay? It diverges. -1 to the power k diverges. All right, that completes that example. Let's move on. Next, we have this theorem, dominance relationships for simple sequences. Okay, this is a very helpful theorem that we can use to calculate certain limits. Okay, here is what the theorem tells us. If any real number, for any real numbers a greater than 0 and b greater than 1, the following string of dominance holds. Okay, what this tells you is that this is the string of dominance. K to the power a is much bigger than, this symbol means much bigger. Okay, this k to the power a is much bigger than ln k, and if you go to this inequality, b to the power k is much bigger than k to the power a, and k factorial is much bigger than b to the power k for k sufficiently large. As long as k is sufficiently large, we have this dominance relationship. Okay. For example, if you take this one and this one, again you can say that factorial k is much bigger than ln k, because see, factorial k is much bigger than this one is much bigger than this one is much bigger than this one. Then this has to be much bigger than this one, right? So that's what this dominance, string of dominance tells us. Okay, so this is very important in calculating limits. I will show you in the next theorem how we use this dominance relationship idea. But now let me show you one limit here. Okay, let's focus on only on this dominance relationship. We know that k to the power a is much bigger than ln k for k sufficiently large. What that tells you is that if you want to find the limit as k approaches to infinity, ln k divided by k to the power a. Suppose you want to find this limit. By this theorem, we know that k to the power a is much bigger than ln k for k sufficiently large. Remember, we take the limit as k approaches to infinity. That means k is getting sufficiently large, right? Then what would be the limit of this sequence? ln k divided by k to the power a. I know that my ak is much bigger than ln k. That means my denominator is much bigger than ln k for large k values. If your denominator is much bigger than your numerator, then the limit has to be 0, right? Having a huge denominator means your sequence is approaching to 0. If your denominator is getting much bigger than the numerator as k approaches to infinity, the sequence should be, the limit should be 0. That's the information that you can get from this string of dominance. Okay. Similarly, we have a set of other limit statements that I will discuss in the next theorem. Here is the theorem that I was talking about. Okay. Convergence of sequences based on dominance ratios. Okay. For any real numbers a greater than 0 and b greater than 1, the following sequences converge to 0. ln k divided by k to the power a, this converges to 0. That means this goes to 0 as k approaches to infinity. This also goes to 0 as k approaches to infinity, so on and so forth. Okay, as you can see, you saw the proof of this one. Some sketch of the proof, because we know that k to the power is much bigger than ln k for k large. That means this whole thing has to go to 0 as k goes to infinity. Okay, that's what I just explained here. Similarly, that applies for the other ratios. If you have a ratio of this form with b is bigger than 1, of course, you need to make sure that b is bigger than 1 and a is bigger than 0. Okay, then again, if you see a ratio like this, that should go to 0 as k goes to infinity. Okay, similar thing holds for the other cases. All right, let's go over the next theorem. Some convergence sequences involving exponents. For any real number p greater than 0, the following sequences converge. Okay, if you have a sequence, this sequence, for any p greater than 0, p greater than 0 is a constant. Okay, any constant which is greater than 0, then the limit as k approaches to infinity, p to the power 1 over k is equal to 1. That's what this tells you. Okay, p to the power 1 over k approaches to 1 as k approaches to infinity. That means this limit statement is true. Similarly, this statement is true. Limit as k approaches to infinity, this quantity is approaching to 1. Okay, and again, limit as k approaches to infinity, this quantity is approaching to 0 for any p, any positive constant p. Okay, now let's look at some examples, and basically the applications of these two theorems. Okay, straightforward applications of those theorems. Okay, the first part. Use theorem 7.15 to 7.18 to analyze the following sequences. Analyze means you need to determine whether this converges. If it converges, can you find the limit, right? Okay, so how do we deal with the first one? Before you deal with the first one, notice that first one is a geometric sequence. This is your R. This looks like R to the power k, right? It is the form of a geometric sequence. What is your R in this case? Let me write this. 999 divided by 1000 to the power k. This is the sequence given to you. Then you can clearly identify your R to be 1, right? R is whatever you have here, right? That's not 1 actually. It's 999 divided by 1000. Now let's go to the theorem related to the geometric sequences. If you have a geometric sequences of this sequence of this form, if the absolute value of R is less than 1, then that sequence converges to 0. In our case, the absolute value of R, what is the absolute value of R? The absolute value of R is, again, 999 divided by 1000, right? It's a positive number. This is less than 1. If the absolute value of R is less than 1, sequence converges to 0. That means limit as k approaches to infinity, 999 divided by 1000 to the power k is equal to 0. That limit approaches to 0 by this theorem. By theorem 7.15. Right? By theorem 7.15. All right, that's about the first part. What about the second part? What theorem can you apply? Well, here I have again put the theorem 7.17. That is that shows how to get certain limits based on the dominance ratio. Okay, notice that this looks like, if you look at here, this looks like this one, right? Pardon me. See, your b in this case, your b is going to be 100. You have k factorial as it is, and you have power k. Your b is 100. right? B can be any number bigger than 1. So by this theorem, we can say that this limit is 0 because all these sequences converge to 0 as k approaches to infinity. Since these two have the same form, we can conclude that limit as k approaches to infinity 100 to the power k divided by k factorial is equal to 0 by this theorem, by theorem 7.17, because this has to go to 0 as k approaches to 0. All right, part C. How do you find this limit? Well, to find this limit, see whether you have something similar here. Do you see anything similar here? Do you see anything that has this form over here? Well, you don't see the exact same thing here, down there here, but if you carefully look at it, you have this, right? It's kind of a upside down thing, right? Here you have k factorial in the bottom, here you have k factorial in the top, and on the other hand, here you have 1000 to the power 10,000 to the power k in the bottom, but here we have b to the power k in the top. Okay, so looks like we cannot straight away apply this one, but we can still apply that by doing some algebra. Okay, this is what I'm going to do. I want to find limit as k approaches to infinity, factorial k divided by 1000 to the power k, 10,000 to the power k, pardon me. This is what I want, right? I'm going to rewrite this limit statement as k approaches to limit as k approaches to infinity 1 over, I'm going to switch the top and bottom now, 10,000 to the power k divided by k factorial. Now, if I simplify this one, I get this expression back, right? I just rewrote the same expression in a little bit different way. Okay, why did I write that way? Once you write this way, now you can take the limit of the top and bottom both separately by the previous theorem that we discussed. Remember, if we have a quotient, this is a quotient, right? This is your top, this is your bottom. So you can apply the limit to the top and the bottom separately. If you take the limit as k approaches to infinity 1, it becomes just 1, right? 1 is 1 itself. What happens if you take the limit of this one? Notice that this limit is 0 by this theorem. See, if we have an expression of the form b to the power k divided by k with b greater than 1, of course your 10,000 is greater than 1, then this limit should be 0 by this theorem. It tells you that it goes to 0. So this approaches to 0. So you get the form 0 plus. Notice that this is a positive quantity. So this approaches to 0 from the positive side. So I put a positive sign here. What is this equal to? This is positive infinity by calculus 1. If you get this form, that means the limit is positive infinity. That means the limit does not exist. Okay. All right, last part. How do you do the last part? For the last part, you can use this particular theorem. This is what exactly you have there. Not that one actually, this one. Okay. As long as your p is positive, p to the power 1 over k is going to 1 as k approaches to infinity. As you can see here, your p is 1 over 100, that is a positive number. This p to the power 1 over k as k approaches to infinity is going to be 1 by this theorem. Limit as k approaches to infinity 1 over 100 to the power 1 over k is equal to 1 by theorem 7.18. Okay, I'm basically applying this part. All right, let's move on. Next, I want to go over this particular theorem, bounded monotonic sequence. This is also a very powerful theorem. Here is what the theorem tells us. If AK is both bounded and eventually monotonic, it can be eventually monotonic or monotonic. This works for both types of sequences, okay? Either eventually monotonic or monotonic. If AK is both bounded and eventually monotonic, then AK converges. That means if we have a bounded monotonic sequence, it is convergent. And if we have a bounded eventually monotonic sequence, that is also convergent. That's what this theorem tells you, okay? You cannot have a monotonic bounded sequence that is not convergent, in other words, okay? All right, let's move on to our next theorem. Convergent sequences are bounded, okay? So here is what the theorem tells you. If a sequence converges, then it is bounded, okay? Whenever a sequence is convergent, that sequence has to be a bounded sequence, okay? We will be not going over the proof of this theorem. All right, next, I want to go over this particular example. Use boundedness and monotonicity of the following sequences to analyze their convergence properties, okay? Let's work on the first one. How do we analyze the convergence properties of this sequence? First of all, notice that from the previous section, from section 7.1, we observed that sine k over k was between -1 and 1. That's the first thing that I want you to observe, okay? That means, what does this tell you? See, your sequence AK, this is your AK, right? This is your AK. Your AK is bigger than or equal to -1, less than or equal to 1. That means this could serve as your lowercase m. This could serve as your uppercase m. Your sequence is less than, always all the terms of your sequence are going to be less than uppercase m, and all the terms are greater than lowercase m. That means your sequence is bounded above and below. Okay, that means sine k over k is bounded above and below. What does that tell you? That tells you that this sequence is bounded. If it is bounded above and below, sequence is bounded. Sine k over k is bounded. All right, how do we find the limit of this sequence? Well, to find the limit of this sequence, we can use the squeeze theorem, okay? We can use the squeeze theorem. To apply the squeeze theorem, first of all, remember, to apply the squeeze theorem, you need to come up with an inequality, right? In the squeeze theorem, you have an inequality there. Go back to it. See, you have a combined inequality, okay? You need to find two sequences, lowercase mk and uppercase mk, so that your actual sequence is stuck between mk and mk. That's what we are going to do, okay? For that, we need to come up with a combined inequality. For that, we always use the property of sine. Sine k is always between -1 and 1. Less than or equal. This is less than or equal 1. Now I'm going to divide each and every term in this inequality by k. -1 over k. K is a positive integer, okay? Then I can divide without switching the inequality, without switching the inequality signs. Sine k over k less than or equal to 1 over k. Now notice that this sequence goes to 0 as k approaches to 0. This sequence also goes to 0 as k approaches to 0. Would you agree with me? Clearly, see, this is -1 over k, right? When k is approaching to infinity, this becomes infinity. You have a infinite denominator. That means this whole thing should be 0. Similarly here, this goes to 0 as k approaches to infinity. Now, view this as your mk, uppercase mk, the sequence. This is your lowercase mk. Notice that your original sequence ak, this is your ak, is stuck between lowercase mk and uppercase mk. And you know that the limit of mk is 0. Lowercase mk goes to 0. And uppercase mk is also going to 0 as k approaches to infinity. Then by squeeze theorem, this middle sequence should also go to 0 as k approaches to infinity. Limit as k approaches to infinity, sine k over k also should be equal to 0. Okay, that gives us the limit. And of course, this is a convergent sequence. The limit is 0. All right, next, let's go over part B. How do you handle part B? How do you find the limit? Monotonic properties. First of all, by section 7.1 again, we went over this example and we proved that this is an eventually monotonic sequence. Of course, it's an eventually decreasing bounded sequence. Okay. K to the power 3 over e to the power k was a eventually decreasing bounded sequence. We proved that there. Okay. Okay, now how do we find the limit of this sequence? Well, to find the limit of this sequence, we can apply theorem 7.17. Theorem 7.17 tells you that if you have a sequence of this form, k to the power a divided by b to the power k, with a is bigger than 0 and b is bigger than 1, then this goes to 0 as k approaches to infinity. Compare this one against this. You have k to the power 3 here, you have k to the power a here. A should be a positive number. Of course, 3 is a positive number. What about e? The value of e, you know from calculus 1, you know that the value of e is 2.7 something, right? So that means it is bigger than 1. Your b has to be bigger than 1, of course, in the theorem, right? That means this should go to 0. That means limit as k approaches to infinity, k to the power 3 divided by e to the power k should be equal to 0. Okay. All right, that completes that part, and I will leave this part as an exercise. It's so straightforward. We talked about we gave a lot of details of this example in the previous section as well. I will leave it as an exercise for you. Okay. With that, we conclude section 7.2. I'll stop there and I'll see you next time.